Thank you all for coming on such short notice. Great pleasure to have Andrew McCallum here. A lot of you know Andrew and his work, but Andrew was the director of research at WhizBang Labs, and then went to UMass Amherst, where he's now associate professor. So the one summer that I spent at WhizBang, I was lucky enough to be there with Andrew and Fernando at the same time, and actually Dave Bly and Drew Bagnell and lots of other people. So, before that, Andrew was a postdoc at CMU. He did his PhD in Rochester. And he's done a lot of great work on information extraction and mining knowledge from unstructured text. And some of you may have seen the site rexa.info. That's a pretty extensive library of academic papers, and it's very similar to Google Scholar. It's mined completely without feeds or partners, unlike Google Scholar. So it's a kind of pure experiment in information extraction, and tries to treat a lot of things as high-level objects. So I think that's a good emblematic of the kind of work that Andrew does. But he's also done a lot of great theoretical work on CRFs and associated learning algorithms, so the whole spectrum. Anyway, the talk will be videotaped, so tell people who weren't able to make it to just grab that off the fish page. And Andrew will be around also for dinner, so if you're interested in joining for dinner, then talk to Fernando.
All right, Sam, thank you so much for the invitation and for the kind introduction and very complete introduction. So it's great to be back at Google. I think this is maybe my third or fourth visit. And I was actually, before coming, thinking back to the first talk that I gave at Google, which was back in 2002. Let's see, I seem to be a little frozen here. Okay, even escape is not doing anything for me.
Maybe I'll fill in with some soft cheese. In case you haven't seen it, there's a wonderful machine learning and extraction library called Mallet, which Andrew and his group maintain and graciously share with the world.
I haven't seen this before, actually.
Java. You can get it off their webpage. And it's got contributions from all kinds of people that you love and trust, like Andrew and Charles and lots of incredibly competent people. So if you're looking for an open source, but sort of almost industrial strength library, you should check out Mallet. All of Rexa is basically built on top of it, so that gives you a sense of the scale at which you can run. How am I doing here, Andrew?
You're doing great, Sam. Thank you so much. It's Microsoft
other
software.
Other fascinating facts about Andrew. Briefly, when he first got to UMass, him and his lovely family decided to build an entire new house, which is absolutely beautiful. If you ever visit, you should get a chance to check it out. But they did the whole planning and everything all from the ground up, and Andrew is kind of in this weird two-body state for a while, where he had like one job as his own contractor and then a second job as an academic researcher. But if you're interested in design principles and what it should look like when you look from your kitchen through your living room to the front door, then you can ask Andrew about that, and in particular about a great book recommendation.
Alexander is a pattern language. Actually, a lot of software engineering people read also. Yeah, fantastic book.
I'm running out of time.
Okay, sorry. Okay, Microsoft is just catching up with me. Okay, here we go. Hopefully this does the trick. All right, so I was thinking back to the first time that that I gave a talk at Google. Hey, Jay. And when I presented, as a representative of WhizBang Labs, actually, a talk on turning the web into a knowledge base.
And you still have the slides?
And I still have the slides from it, all the way back then. And which was essentially about extracting objects from the world. I was actually here as somewhat part of a secret mission to try to get Google to buy WhizBang. And the answer that we got was essentially, well, we really don't think that that Google's really ready to buy any companies, and so we won't. You look very attractive, but and of course, things have changed a lot at Google since 2002. So I argued at the time that this is also a slide from that previous presentation, that it's often the case that that people are searching for pages, but people are also very often what they really want to find is an object. They want to find a company or a person or a course, and they want to be able to do this search in specialized ways. And one piece of evidence that this is in demand are that there exist sites out there that support very object-specific search. This is a website that supports search over companies. This is actually an old slide. You can tell the company's name has changed. Elion.com now. ZoomInfo does search over people. This is a search over courses offered at universities all across the country. And why would we prefer thing or object search over paid search? It offers you a targeted, restricted universe of hits. So don't show me resumes when I'm really looking for jobs. The vocabulary might be the same, but I'm looking for jobs. You can do specialized queries that are topic-specific or based on multidimensional features or information that's spread across multiple pages. You can get the correct granularity, and you can provide some specialized display in a way that's super targeted for the kinds of slot values that these object types present. An additional attribute that I've always found especially fascinating is that once you've extracted information about structured objects, you can do traditional kinds of data mining on this structured data to find patterns, found outliers, provide very targeted kind of decision support. And let me just give a few examples of this combination of extracting structured knowledge and doing data mining, and then we'll move on to some technical items. So the first thing that we did at this company, WhizBang Labs, was to build a system that extracted information about job openings directly off of company websites. The system would begin at the homepage of a company, automatically navigate through it to find the section where they list their job openings, and use some statistical machine learning methods to segment the job openings from each other, automatically extract the job title, the description, area of the country where it's offered, contact information, etc. And we launched a website, which scared the pants off of Monster because it had more than twice as many openings as theirs did, and provided a very structured, targeted kind of search in which you could specify exactly what you were looking for and get back a very targeted, nicely presented set of results, exactly in terms of job title and company and date at which the posting was first placed on the web, et cetera. But part of what I found most fascinating is that then now, once we had this large database, is that we could mine this database. And in fact, we did that once a month. WhizBang ran various data mining algorithms and discovered job trends across the country. High-tech jobs rising in the South and falling elsewhere. And we actually heard anecdotally that several state and local governments were using this data to help set governmental policy because nowhere else could they get data that was this comprehensive or up-to-date. Just a couple of more examples. Back in the late 90s at Carnegie Mellon, I built a system called Kora that did information extraction from research papers. We would take the PDF, convert it to text, use some machine learning methods to extract titles, authors, institutions, abstract citations, et cetera. And here's a screenshot of what we built. Of course, now there's Sighteer and Google Scholar and others. And this also not only allows you to do search for research papers, but also to do some kinds of mining. Here's a very limited kind that comes from Sighteer. It's the list of the most highly cited authors in computer science, modulo some person co-reference errors. And here's something a little bit fancier. You can run some topic models over the text of the papers to discover different research topics and also the people who are associated with those. So here, this topic, handwritten character recognition. You can see here the system is saying that Patrice Simard is a good expert in this topic, which is actually true. And lastly, a project that we've considered at UMass is working with data that looks like this. The Chinese Academy of Sciences has a few 100,000 documents that are literally several millennia old. They're Qing Dynasty archives, memos, newspaper articles, and these contain a wealth of information about all kinds of topics, and one of them is the weather. People in these articles talk about, my cherry tree bloomed early this year, or my crops have flooded, and my fields have flooded, and my crops are bad. And these are scientists who are trying to understand long-term weather trends, and this data is so valuable to them that they're having humans go through these documents to extract information about weather events, but they're having a little bit of trouble. And so we've considered are there some ways that we can use automated methods to help them out. So as a precursor to this kind of mining or object search, we need to take raw, unstructured text and turn it into objects, which is what we call information extraction. Right? We start with some text like this. and a database with the fields defined, and we want to extract from this text the information to fill those fields. And as a task, this involves doing segmentation to find the boundaries of the text regions we're interested in, classification to say that this is a company name, this is a job title, this is a person's name, association to say this person had this title at this company, and then clustering or deduplication to collapse duplicate information so we don't get a messy database with a lot of duplicates. All right, so people have been using machine learning methods to address all of these steps. And in some cases, there are even relatively accurate examples of how we can do these well. And you might think that if we had 90% accuracy at all of them, that we'd be quite happy. But this is wholly insufficient. You get a complete mess at the end because through this processing pipeline, errors compound. And if you take each one of these 90% accuracies in each one of these steps, you really are only getting 60% accuracy at the end once you've done the multiplication. So for this reason, for years now, I've been advocating the desire to do more joint inference through this pipeline as well as other natural language processing pipelines. Reason about uncertainty, pass multiple hypotheses and uncertainty through this pipeline so that later stages of the pipeline can help us correct earlier stages, et cetera. And if we think even about just these first two steps, segmentation and classification, part of the magic of a finite state machine is exactly that it does these two steps jointly. It's simultaneously reasoning about where to put segment boundaries and how to label things. And that's, I think, one of the major reasons that they're so popular. Our larger research goal is to pull them all together, and even furthermore to combine reasoning about the database building part with reasoning about the data itself. And I've talked about that before. In fact, I think the last visit I was at Google, I talked about this kind of joint reasoning. What I'd like to do today is first briefly revisit the kind of models that we've been using for the last several years for these first two steps, and then really the technical heart of this talk will be to focus on the very last step, the clustering or the entity resolution step. Okay, so along with Fernando and John Lafferty in 2001, we were looking at various finite state models, and that in combination with the desire to train them discriminatively rather than generatively led us to these models called conditional random fields, which which here in its linear chain form is represented by a finite state machine. Here's the graphical model. I'm not going to give a tutorial on conditional random fields. Suffice it to say for now that you can think of them in this linear chain form as like a hidden Markov model that's trained discriminatively. It's like logistic regression where the output space is not a single label, but an entire chain of labels with Markov dependencies among them. And they've proven very successful experimentally, not just in language processing, but in bioinformatics, where Fernando has the world leader in gene finding based on linear chain CRFs, as well as in computer vision and many other areas. Okay, so this is a certain kind of CRF. And here's an example of the kind of experimental difference that it can make when we look at this problem of extracting these various fields from the PDF of a research paper. Hidden Markov models, we're getting accuracy like this. Another discriminative training method based on support vector machines, but one that doesn't really fully capture the Markov property very well, is getting accuracy like this, and a linear chain CRF is doing much better. All right, okay, so now I want to get to the technical heart of the talk and talk about this clustering method. So here's the plan. We've just talked briefly about information extraction at a high level and about conditional random fields. I'd now like to introduce the entity resolution problem and talk about three different basic ways of setting up the problem, as well as some particular technical details for how to get it to perform well. And then we'll also talk about schema mapping, and then we'll see how much time there is to briefly talk about Rexa at the end. Okay, so We'll start with entity resolution. So this linear chain conditional random field is, of course, not the only shape of conditional random field that you can have. They can come in all kinds of different shapes. And we're going to talk about one that's quite a bit more complicated than just a linear chain to address coreference or entity resolution. So first, let's just dive into the details and make sure that we're just all on the same page and sharing the same vocabulary about what the problem is. Coreference resolution has many names. It's, itself, in different fields, it goes by record linkage or database record deduplication or citation matching or object correspondence or identity uncertainty. It's sort of an in-joke that the research field that itself is concerned with resolving many different names for the same object itself has so many different names. But I think this is really because it's such a ubiquitous problem that it arises in many disparate fields separately, and they've each named it separately. All right, so we're going to, for now, talk about this problem in the context of doing somewhat classic natural language processing coreference resolution among the entities that appear in a Newswire article. But these same methods apply to record linkage in other kinds of structured databases, and I'll show experimental results from that kind of data later. So the input is a news article with the named entity mentions. These are already tagged. So here I see mentions of people, Secretary of State Colin Powell, he, Condoleezza Rice, et cetera. And it's my job to produce as output how many different people are being discussed and which mentions fall into which clusters, or which mentions are referring to which separate person. So it's a clustering problem, and it's a kind of clustering problem in which I don't know how many clusters I should have. The traditional solution for this method is to build a pairwise affinity metric. You take two mentions, and you're asking yes, no, are these referring to the same person or not? And you do that by considering many features of the pair, of the contents and the context in which these mentions occur. And you learn weights associated with those features. You take the features that occur in this one particular pair, you sum up their weights, and if that sum is above some threshold, you say, yes, they're coreferent. And you take connected components and the graph of these decisions and declare the partitioning that you found to be your favorite. So let's just, I want to draw this problem pictorially. I'm going to build on this representation later as I talked about several different kinds of models. Here we have 5 mentions, strings that are referring to people. And the question I'm trying to address is, well, how, so I'm going to call these mentions of people. And the question I'm trying to address is, how should I cluster these mentions? Or is it the case that these 3 mentions are referring to one person and these are another entity? Or should I cluster them this way or this way? I don't know. I need to figure that out. Okay. So here is a picture of the traditional model. Anyway, these pairwise affinity functions are represented by these black boxes. You can think of this as a factor graph where, well, maybe we'll put the factor graph thing off for a bit. Sorry. This is the function that's asking, is this pair of mentions, are they referring to the same object or not? I'll get a score, I'll sum it. If it's above some threshold, then I'll color this edge green, and I'll take this label, I'll put this label inside this circle here, meaning coreferent. Yes, I think they're coreferent. Here's a sum that was below threshold, I'll color it red, and I put the not coreferent label here. All right, so let's think about how the traditional solution works on this problem. Let's see, I'm saying Mr. Hill and Dana Hill are the same person. I'm saying Dana Hill and Dana are the same person. I'm saying Amy Hall and she are the same person. And there's also something about the local context that makes me think that she and Dana are also the same person. So I take connected components in this graph, and what have I just done? I've said that they're all coreferent, which seems a little unlikely to say that she and Mr. Hill are referring to the same person. So something seems terribly wrong here. What's the problem? Well, I'm making these pairwise merging decisions independently from each other, when really I should be making them jointly in dependent relation with each other. So I'm going to take this problem and treat it instead as a conditional random field, in which I'm going to make pairwise merging decisions jointly across the entire model. I'm not going to score and locally normalize individual pairwise decisions. I'm going to jointly normalize over the entire graph all at once with an equation that looks something like this. This is a decision over not just a single edge label, but the labels over all edges in the graph. And my score function for this is determined by some weights that look at pairwise features, and then also some other part of the model that I'm going to add that wasn't there before that looks at triples of these labels to make sure that they obey the transitivity property. I want to express this notion that I'm not allowed to say in some triangle of mentions that, well, these two are co-referent, these two are co-referent, but the other edge of the triangle is not co-referent. That's just not allowed. And I'm going to represent that with some function that examines these triples and some non-learned weight here that's just negative infinity to say that I don't like that. So as I consider scoring the entire model, I gather together the sums of the scores on all of these edges, summing over all of ij. So let's make this concrete. I'll put some weights on those edges. I've just drawn them. I'll sum over all of those. I get here's the score for how much I like each one of those individual edge decisions. But I violated transitivity, and so this part of the score is negative infinity, and this one doesn't even really matter. So this is one set of labels on edges that I don't like, that gets a low score. Really, the problem is here, or another way to say this, if I change the label on this one edge, then I no longer violate transitivity. So let's go ahead and do that. Even though locally this edge is saying it would prefer to be connected, to be a yes, let me change it to a no, which simply involves changing the sign on this weighting function. And now I'm no longer disobeying transitivity. This negative infinity goes away and just is replaced by a 0. And I'm actually, just for the time being, not going to draw these three-way factors anymore. I mean, I was only ever really drawing one of them, although there would be many of them in the graph. It was just for the sake of clutter. But to completely get rid of clutter, I'm just not going to draw them for now. And this coreference decision is represented by this partitioning. And I can also now ask about the score that I get by summing together all of my edge weights, and I get some other number that's a little bit lower than before, but still looking pretty good. So this is the score I get for this configuration that obeys transitivity.
So Andrew, can I just ask about
yes.
that? Why does the no decision between Amy Hall and Dana not violate transitivity there? I'm looking at the yes triangle between Amy Hall and she and Dana.
Okay, so don't look at the color, but look at the letter label inside the circle. So
well, that's the one you just changed.
Yes, that's right.
Okay.
Sorry. Yeah. So it was violating before, and now it isn't. Yeah.
But
yeah,
you
thanks.
don't actually instantiate these potentials, right?
Okay,
you just
so that's
somehow do it in the beam search or something.
Yes. So you're absolutely right. There would be a lot of triples. I mean, I'm going to talk extensively actually about how to make this really scalable, and we actually run these algorithms on our data from Rexa, where we start with. Well, the slide will say, but it's many millions of mentions and do co-reference on this. And these factors are part of the definition of the model, but in the engineering, they're never actually really instantiated. Okay. So part of doing inference is to consider multiple partitionings and to get the scores for all of them to see which ones we prefer. So for example, I mean, this is just one partitioning. I could change some of the C's and N's. Here it goes, right now. And this is another coherent partitioning that is this one. And as I changed those C's and N's, I also changed the sign in front of the corresponding edges. And so I can get a new score for that. That score is -12. I definitely don't like this as much. So I prefer the other partitioning to this one, which makes sense according to the scores. All right. So as these drawings and examples are designed to make clear, this is actually a special kind of CRF, or Markov random field, in which inference corresponds to graph partitioning. It's a kind of graph partitioning with both positive and negative edge weights. and it's been of significant interest for a while. It corresponds to this kind of clustering called correlational clustering that Avram Blum and others have been talking about for a while, and Eric Demain at MIT has become quite interested in. And so there's a whole theory community that has been interested in algorithms for partitioning these graphs. It's an NP-complete problem. I mean, unlike the case where you have only positive edge weights, where you can solve that exactly. When you have negative edge weights as well as positive, it's NP-complete. But there's some nice approximate algorithms that we can use that come out of the theory community, which we can leverage. All right. So one of the main points that I want to make today is that now we're going to go beyond what I've just been talking about. Yes, Fernando.
I'm a bit confused. So the correlation clustering and in the stuff based on what's about
the Jianpo-Shi, et cetera.
Yeah.
Yes, right.
All of those are just for pairwise. They do not.
That's right.
There is no, as far as I know, there is no extension of those. Say the approximation results, for instance, for metric partitioning, which is only for positive ways.
Yes.
Don't generalize for anything beyond pairwise. I don't think.
No, that's.
And for correlation clustering, I don't think they do either, right?
Well, can we make sure I'm following you? So yeah, the work above is actually work that's making the correspondence between Markov random fields and these kinds of partitionings. And yes, above the space are only positive edge weights. Right. That's correct.
Yeah.
And right. Yeah. So this lower one is using negative edge weights as well. And what's your question
for
about?
Edges, there are no hyper edges.
That's correct. And so in nothing that we've talked about so far are there any hyperedges. I'm about to begin to talk about hyperedges.
You had the blue.
Oh, in those. Oh, I see.
I'm kind of confused about the connection. The sort of
the connection to Markov random fields.
To those things on the upper right.
On the upper right. That yes. So that connection may be more loose. You're right. You're correct about that. Yeah. I mean, the stronger technical connection is to correlation clusters.
Because once you go to hypergraphs, everything falls apart. As far as I know, all of that stuff kind of collapses into a pile of
Yeah.
short
right.
shards, basically.
Can you be more dramatic?
Yeah, good. Yeah, yes.
Okay.
Okay. All right, so now I want to talk about why pairwise affinity is not enough, and not just in terms of obeying transitivity, but in a deeper sense. And to make this point, I'm going to change the example slightly. First, let me clean up. I'll get rid of the numbers. And I'm going to change these mentions to all be she. Okay. So here I have some partitioning. Let me see, what do I have here? Yep, it corresponds to this one here. And at first, this seems to be a pretty good one, right? Amy, Holland, she, that's reasonable. And I'm not violating any gender transitivity here. It seems quite reasonable that she and she would all be in the same partition. But as we think about it further, we think something is a little strange here. Here I have a newspaper article in which there is a person who is only ever mentioned by pronoun. Nowhere in this newspaper article do I name this person, which seems incredibly unlikely. Yes, that's right. But even still, you would think. Yes, that's right. So this is a kind of partitioning that I would like to give a low score to. But there's no way in the current model to recognize that something is fishy here, because I only get to look at pairs. I only see that she and she are together. That seems reasonable. These two she's are together, and these two she's are reasonable. But nowhere do I get to see, oh, here's a partition in which everything is a she. Everything is a pronoun. So this model is just not going to let me see that problem. And this is just one example of cases where pairwise comparisons are not enough. So what would I like? I mean, I'd like to have some feature that asks the question, is it the case that all mentions are pronouns? In other cases, I don't know, where I'm doing database record deduplication, I may have mentions that have multiple attributes, but not all those attributes appear on every one of the mentions, and I want to measure compatibility among all of those attributes, but they only really all come together when I consider them all at once. Or there are other cases where, as you're looking at names of people, there can be some ambiguity about what is a first name and what's a last name. And I could look at every pair of these people names and decide that, well, there's some reasonable chance that they're referring to the same person, except that if they were all referring to the same person, there's no common agreement about what's a first name and what's a last name. And another way of putting this is that, having 2 given names is pretty common, but having 4 given names is not common at all. And there's just no way to see that that's the implication of doing this co-reference decision if I only get to look at pairs. There are other cases where I might have expectations about the sizes of the partitions, and there's no way to see that when I see only pairs. Or I may also want to ask, there may be a lot of edges that are nicely weighted, but I want to ask the question, does there exist in this partition some pair of last name strings that differ by some threshold? All right, so I want something more than pairwise. I want to be able to ask there exists and for all type questions about the entire set of mentions that fall in some partitioning. What I want to be able to ask questions in first order logic and to give weights to the answers. And this is exactly what we're going to do. Okay, so now we're going to talk about pairwise affinity and the combination of probability and first order logic. Let's see here. Yeah, so probability and logic have been 2 branches of artificial intelligence that have long been separated, and there have been recent efforts over the years to try to bring them together, and this is one of those examples. You can think about this as a conditional random field in which the parameter sharing is defined by clauses in first order logic, and we assign weights to these clauses. So what I want is a factor graph that looks like this. Instead, I'm going to have some affinity function, and rather than looking at a pair, it's going to be connected to all mentions in a partition. And then I can ask arbitrary questions. Inside this box, I can ask arbitrary questions about the whole set. Okay, so this factor graph represents the functions I would have to measure for one particular entity resolution decision or partitioning. And of course, doing inference involves considering many possible answers and scoring them all and seeing which one I like best. I could consider that this might be the right co-reference decision and want to evaluate that function, or this one, or this one. There are a lot of them that I might want to ask. Right? How many do I need to evaluate? Well, how many different ways are there to divide 5 items into subsets? There are a lot. And the issue is that and furthermore, I'm going to be working with news articles in which there aren't just 5 mentions, but there are, on average, about 200 mentions. And so this is going to get very big, very, very fast. So this kind of space complexity is common in probabilistic first-order logic models. Other people who've been trying to bring together probability and first-order logic. So one of them is various people who have also been learning weights on logical clauses, where you describe the world by making some statements in first-order logic, assigning weights to those statements. And part of doing inference in this model is to so-called unroll the network or to ground the network to fully instantiate all the possible outcomes and the variables that should get assignments. And doing so requires a lot of space. It's space exponential in the arity of the clauses. So we're faced with this question: how can we perform inference and learning in models that can't be grounded? Right. It's not just a question of not having enough computational power or time to visit all the different configurations. I mean, I don't have a prayer of fitting them in memory. So how can I perform inference in this case? So let's look at what some other people have been doing. Some of the early work here involved saying, well, let's only work on small data sets where we actually can completely unroll the network and fit it all in memory, and people who used weighted SAT solvers to do inference here. There are some more recent alternatives in which you can save memory by only storing clauses that may become unsatisfied, but there are still some time problems here. The initialization for this algorithm still requires exponential time to visit and evaluate all of those ground clauses. So another broad family of approaches are Markov chain Monte Carlo methods. in which I don't try to unroll the entire network all at once. I essentially just visit a single configuration at a time. So one simple example is Gibbs sampling. I pick one possible output, and then I visit a single variable, or maybe a small neighborhood of variables, and sample some new values for those. But the problem in so many applications of Gibbs sampling is that it can be quite difficult to move between high probability configurations by changing single or a small set of variables. So you can get quite thoroughly stuck in local minima. So we have been advocating for some time a different inference method, an inference method based on Metropolis Hastings, which is another MCMC method. And what's special about Metropolis Hastings? Well, it comes in two parts. There's a model probability distribution that you have traditionally, and then also a proposal distribution. You can think about this as some jump function. Metropolis Hastings can be extended to partial configurations in which the model is only partially instantiated. It's been successfully used in generative models that combine logic and probability, the blog work by Brian Milch and others. And the key advantage that I want to plug here for Metropolis Hastings is that it lets us design sort of arbitrarily smart jump functions. So let me just make the picture of what's happening clear and then explain further what I mean about this advantage of arbitrarily smart jump functions. So rather than representing all possible configurations and scoring them all, I'm only going to represent a single configuration at a time. I can fit this in memory. And I'm going to decide which configuration I like best by doing some random sampling. I'm going to use my proposal distribution or some stochastic jump function to say, well, I'm starting here. Let me make some change to that suggested configuration to make it look like this instead. I'll score this jump to decide how much I like it. And if I like it, I'll stay here and further explore from here. And if I don't like it, I'll go back to where I started, or back one step, and propose a different jump instead. OK, so what does this jump acceptance probability look like? It consists of two ratios. There's the ratio of how much do I like this new configuration more than my old configuration, as measured by the full parameters of my model, as we saw earlier with all the brown number scores. And there's also a ratio of transition probabilities to the new state from the old one and vice versa. So what are some nice things about this? So first of all, let's just note in passing that since I'm only considering ratios of scores, the partition function, which is so difficult to calculate, just cancels and is no longer a problem. This also means another very nice property is even when we only instantiate one configuration, there are often many, many factors that we would need to evaluate in order to fully score the model. But I can even skip evaluating those. I only need to visit the factors that have changed between these two configurations when I consider that ratio. OK, so the other part of this is the proposal distribution. This is the probability that I would propose some jump from one configuration to the next. And what's the purpose of this? Why is this in Metropolis Hastings? This is a ratio that makes up for any biases in the proposal distribution. And maybe I can motivate it by drawing the following picture in the air. Imagine that you're trying to do a simple kind of optimization in which you're just changing a one-dimensional variable. And there's some optimization surface on top of this 1D space that you're trying to do inference or optimization in. And you've got some sort of jump function that's somewhat biased. And it tends to jump left a little bit more than it jumps right. If you didn't account for this bias, you would spend a lot of time exploring the left-hand region of the space and not enough exploring the right. And you would not do a good job. So let's see here. So what's nice about this? This means that I can design sort of arbitrarily smart proposal distributions, which will inherently be biased, knowing that the mathematics is going to take care of that bias for me. So if you think about the many variables that are involved in doing coreference resolution or various other kinds of fancy inference, if I try to just change a single variable at a time, I'm going to invariably mess up transitivity. We can get quite creative and very targeted in designing very specialized jump functions and really leverage that significantly to do a better job. Let me maybe, I don't have a slide for this, but make another example of where smart jump functions that are inherently biased can be useful. We've been looking at dependency parsing that is based on factors more than just parent-child weights in the parse tree that consider more global kinds of score functions. And that's, again, a case where we can't do exact inference, and we're doing inference by an MCMC method like this. And one of the properties that we want to preserve in the dependency tree is that is projectivity, that the parent-child lines in the tree don't overlap with each other. And so we essentially initialize with a projective parse tree and then highly design some jump function that preserves projectivity, which is, is a little tricky and takes a little bit of thought, but it's not that bad. And but it does produce jumps that are biased in certain ways, and so we can do this knowing that Metropolis Hastings will take care of these biases.
I'm a bit confused about whether the goal here is search and optimization to find a single configuration which has good score under the posterior, or whether the goal is to sample correctly from the posterior.
Yes, okay, good. I knew you would ask this, and I'm glad you did. Yeah, so Metropolis Hastings is really designed as an inference algorithm and not as an optimization algorithm. And the answer is that, well, we're interested in both. And there are cases where we would really care about the marginal and we want to do inference. There are a lot of cases also where we just want to find the highest scoring function. But I would like to argue that the interest in being unbiased appears in both of those cases. Or maybe another way of putting it, and I'd be happy to argue about this, is that we are doing a kind of optimization where you take samples from the posterior and then do, say, local greedy hill climbing from each one of those posteriors, and getting good samples from that posterior that are unbiased is a useful precondition to have. Okay, we can take
it off.
Okay, all right, okay.
I'm pretty sure that maybe we should just ask you this directly. Do you have any evidence that this actually mixes?
Yes, and we can take the rest of that on. Yes, good. Yes, yeah. Okay. All right, so Metropolis Hastings lets us freely bake in domain knowledge about fruitful jumps, and it takes care of these biases. It avoids memory and time consumption with massive deterministic constraint factors. So as in the projective parse tree case, or as in preserving transitivity, we simply build jump functions that avoid legal states. I don't have to add factors to my CRF that disallow violations of projectivity or transitivity. I simply build jump functions that make sure that I avoid those. And also, since I'm always using ratios, I only need to calculate the factors that differ. All right.
Are you going to say how you're going to estimate Q? I wasn't sure of how.
Oh, excellent. I don't have a slide for this, but that's a fantastic question. And if you, Brian Milch has told me one-on-one that designing good proposal distributions is one of the trickier aspects of using blog. And one of the things that we've been doing here is, let's see here. Essentially, we're going to learn some of the parameters of the proposal distribution as well as of the model scoring function. And we're going to do that by having the proposal distribution share some subset of the parameters of the model scoring distribution. So, the proposal distribution needs to be something simple enough that we can calculate both the forward and backward jump probabilities. So it's not fully parameterized the way that the model scoring function is. But the fact that it shares some parameters means that as I learn a good scoring function, I'm also learning a better proposal distribution. All right. Okay, so we've talked a little bit about inference, and now I want to talk about how to do learning, how to learn these weights on these clauses. So let's just set up the problem, right? The input for this learning problem is some set of first-order formulae and some labeled data. And I want my output to be weights on each one of those formulae. So I want to learn likelihood ratios that will lead to good coreference decisions as defined by my labeled data. And so the traditional way to do this is essentially to borrow the techniques that have been used in all kinds of other CRFs, linear, chain, and others, which is to calculate a gradient of the log likelihood of the true labels in some labeled data. Which in turn requires expectations on marginals, and we can get marginal distributions by sampling according to some MCMC method, but it's really inefficient due to this incredibly large sample space. And so what we're going to propose instead is using ranking, learning by ranking, rather than classification, simply to say, well, I prefer one configuration over another. So pictorially, or as an example, this looks like this. Instead of training the system to look at some partition of mentions that I'm currently hypothesizing as being all coreferent, and to issue the correct label to say, yes, this is a good partition, or no, this is a bad partition, I'm instead simply going to learn, well, this partitioning is better than this one. And other reasons that I like this is that it's often the case that we're looking at partitionings in which neither one of them is correct, but one is a bit worse than the other. So here, George shouldn't be in either one of these, but having he and Mr. together looks a lot better than having she and Mr. together, so I like this one better. So how are we going to do this? We're going to use a large Martian update based on Myra. And the algorithm looks like this. We have some observed data. We know what the true labeling is. We have some prediction algorithm. This is essentially our inference algorithm based on Metropolis Hastings, and some initial set of weights. I essentially run my inference algorithm to get some new state that I'm saying I'm going to accept, and if according to my current parameters, and if this configuration is actually according to the true labels worse than where I came from, even though my score function thinks it should be better, then well, clearly here my score function, my weights are telling me something wrong, and I should do an update. And so I'm going to update my weights based on the improper acceptance of this jump. And and this update is essentially considers where we're coming from, considers the bad jump that was proposed, looks at the truth to generate some jump that indeed would have been better instead, and updates my weights to try to produce the correct ranking among those two alternatives.
So Andrew, I mean, it just goes back
yes.
to Heinz's question. The proposal distribution could introduce a problem here, right? Mm-hmm. Because you might not be sampling the things you want to compare in a sufficiently unbiased way. Right, so because you're going always to say, well, I have two alternatives, A and B.
Yep.
And that I'm going to compare.
Yep.
But the ones that you are given to as training instances, effectively, are the ones that are generated by a proposal distribution. So, how sensitive is the learning to the proposal distribution? You see what I mean?
I said maybe I'm not quite seeing the problem. Actually.
Because the proposal distribution line is sampling over possible configuration.
Yes.
And those configurations are the ones that you're then going to use to adjust your scoring function.
Yes.
Your P.
Yep.
Essentially, or the ratio of P.
Yeah.
And one worry would be that the proposal distribution might be kind of myopic in some way, or mm-hmm. And just focus on the very small set of the possible instances that you might see.
Well, okay, so I mean, it's certainly true that our proposal distribution may not be ideal, and maybe that's improved because it's sharing some parameters with the scoring function, or maybe it has some inherent limitations, but that's a separate problem. I mean, what I see here that I like is that the inference algorithm that I'm actually going to use in practice at test time is the one that I'm using during training. So the kinds of rank comparisons on which I'm going to be training are the kinds that I'm going to be faced with when I'm actually running my inference algorithm at test time. And I'm learning to make those better.
Right, I like that, but I'm wondering whether there's something that if you are a little bit, if you're not really careful about what Q is, could you sort of get
Well, I think, yeah, I mean, if Q is fundamentally myopic, as you were putting it,
Yeah.
or broken, then yeah, this is not a learning procedure that's going to escape from that.
It's a way of evaluating this, I guess that's the question, of deciding.
Evaluating, you say, your choice of Q?
Yeah.
I mean, other than by sort of the final accuracy, or you sort of essentially, well, let's see here. Well, okay, so I mean, another thing that I like is that, right? We consider the Q prime that was proposed, that was given by my proposal distribution. Mm-hmm. The other one that we're going to compare it with is actually a Q that I generate by looking at the truth, right? So in as much as the parameter, the setup of my proposal distribution and its parameterization would allow me to consider better jumps that I could arrive at by considering the truth, then I think this is going to steer me in that direction. So I'm not just comparing where I came from and where I jumped. I'm comparing my incorrect proposed jump with something that's better as defined by the truth. So that makes me feel even better, actually, about this in relation to your question. Okay. All right, we're just about done with this. So this is a summary of where we are. We already read through these advantages of Metropolis Hastings, and here we're doing learning by ranking, right? So don't train on likelihood, train to properly rank configurations, which has a number of nice properties. And here are some results that we're extremely excited about. On one of these standard data sets of Newswire articles from the DARPA ACE program from 2004. This is one of these data sets that the NLP community has been beating its head against for quite some time. As you can see, actually, in the world, the best in the world performance over time. In '97, we were getting about 65% F1. A few years later, we were getting to 67. A few years later, 68. These may seem like small changes, but the natural language processing community is incredibly empirically driven, and these are like major results that people are excited about. And in 1 year, we jumped from 68% to 79%, and we were pumped. And where does that benefit come from? Well, here you can actually see that based on our own features, we were doing even worse than the state of the art. So maybe we could do better with more feature engineering, which is often the case. We get some jump from using, instead of a pairwise function, a partition-wise function. And we get also some jump by using rank-based training instead of likelihood-based training. And these kinds of results carry over.
So Andrew,
yes.
It's kind of really interesting that even the bottom row there.
Yes.
Right, that just the rank-based training without the new representation gives you a better improvement than anything else that people did since 1977.
Yes. Yeah. And I think we're still trying to understand that, actually.
Which is really puzzling because it's just purely an algorithm.
Yes.
And search issue that has nothing to do with.
Yeah. Well, it's. I mean, Claire Cardi and others have done experiments in the old style co-reference resolution in which you just sort of, subsample the negative edges in your training and things like that, which can make a big difference. And so I think it's some flavor of that's going on here, and that these people were not maybe training on too biased a sample, or too many no edges or things like that.
Training is closer to what you evaluate yourself at test time with, right?
Perhaps there's that too.
I mean, who cares about likelihood?
Yeah, I know.
Yeah.
Still.
So we also obtain improvements in data that doesn't come from NLP, that comes from databases. So here is a database of mentions of research papers. There are citations that appear at the end of of research papers, and they've already been pre-extracted into 14 different fields of titles and authors and venues and years and volume numbers, et cetera. And we're getting a 30% reduction in error. And we also do co-reference over research paper authors, which is an incredibly hard problem. And we find some improvement there also.
Have you solved my problem?
No. So, we're working on it. And it's better than it used to be. The Fernando Pereira in Portugal that works on video compression is still a little bit confused with you. But
stop his email coming my way.
yes, that would be great.
Can I ask you about the features a little bit?
Yes.
So all your examples didn't include any definite references. They were names and pronouns. And
Right. So the examples didn't include those, but the ACE data set includes common nouns like the president and things like that. And so those are included here. And the features are fairly standard at this point. They're some string overlaps and various flavors of string edit distance and number and gender agreement.
Like knowing that president is an officer or those kinds of things.
Yeah, let's see. I mean, some people I know use features from WordNet and other places, and I believe that we did also. I don't think their innovation is in the kind of features that we use.
Yeah.
Okay, but yeah. And I have a slide that I can show you offline in which I actually lay out those features.
You should press forward, because
Yes,
we're almost
okay,
out of time.
that's right. And in fact, the rest of these are really a lot shorter than they used to be. So another configuration of the model that you can make for doing entity resolution is a different one. It's one in which the factors don't compare mentions against each other. We infer some canonical representation of the entity in sort of a database record form and measure compatibility between the mentions and the canonical form. And this is a type of entity resolution that we've been very excited about recently. Not only because I think it has some interesting properties in this function, but also because a byproduct is that it gives you canonical values for what you would put in the database. And in various tests, it actually works better, even better than the partition-wise affinity. All right. So the thing that we've been doing most recently is trying to step back to an even larger part of the information extraction problem that includes schema mapping as well, in which as data, you're given multiple databases, each of which come with a different schema or layout of what the fields are, and these fields overlap with each other, but in all sorts of strange ways, and you have to resolve them against each other. And in particular, we've been doing joint inference through these three highly intertwined problems of entity resolution or co-reference, deciding on those, deciding on canonicalization. Here are all these mentions, including some misspellings. What are really the canonical values in which I would put in a single record? And schema mapping. Here I have 4 different databases that are referring to overlapping information, but in not well-aligned ways. Here, name, presumably first, middle, and last name are all going to appear as a single string in this one field, but here they're split across into 3 separate fields. Address is collapsed here, but not here. Gender doesn't appear here. Email only appears in one place, et cetera. And I want to resolve all these together. And you can imagine how decisions in each of these 3 different problems are highly intertwined with each other. And so doing this problem jointly, preserving the uncertainty from one task to the next would do well. I'm not going to describe this in great detail, but it's another factor graph, very much in the flavor of the previous one, in which I have the factor graph as I did before down here for entity resolution, where I'll do partition-wise wide scoring. And here I have another, it's a little bit like entity resolution. It's just the entities are fields in individual databases, and I'm trying to decide which fields are referring to the same underlying information. And I have factors that describe how these 2 problems interact with each other, and I solve it all jointly using Metropolis Hastings. And we've been trying this on data of contact information, records of contact information for people as they appear as they are on the web. So we gather these from department faculty listings, alumni listings, and extracting address blocks, et cetera, off of home pages. There are about 14 fields in some of these databases, 3 fields in others, and there's just a surprising variability. and we get some very nice results that show that when you do indeed do this problem jointly, that you get some real benefit. All right. That was coreference resolution accuracy. We also get better schema alignment. This is the result of schema alignment when you do a cascaded approach, where you do coreference first and then do schema alignment later, or actually is it the other way around? I'm momentarily forgetting. The green lines are the ones that are correct. The red lines are incorrect, and here we do much better when we do this task jointly.
This assumes you're going to find one-to-one alignments only?
No, so actually, let's see here. So there are some other ones. I mean, we could talk more about the details of this offline. I don't have a lot of detail on the slide. But to answer your question briefly, the model is not restricted to just one-to-one alignments.
When you're resolving entities, right,
Yes.
there's one-to-one correspondences, right?
Right, right.
Well, now when you have schema elements, you can have one schema element that corresponds to a set of schema elements, so the same, something doesn't map over.
Yes, that's right. So there are aspects that don't map over, but our current model is allowing that lack of one-to-one correspondence. Yeah. Okay. All right, and so now maybe just very briefly, I'll talk mostly about the scalability aspect here. So we have been applying these ideas in practice to data that we at least consider large scale, although I'm sure you wouldn't. And this has been in the context of building enhanced alternatives to some of these older systems that are research paper search engines like Kora and Sighteer and Google Scholar, where our main aim is to not only recognize research papers as entities with citation relations among them, but a much richer universe of object types, including people and universities and publication venues and grants and groups and expertise, et cetera. And building the system involves a pipeline that spiders PDFs from the web, converts PDF to text, uses conditional random fields to do information extraction of many different fields, does reference resolution of papers and people and authors and now grants to venues and institutions, and then we do various kinds of data mining on this data. And currently, we're working with about 60 million mentions of papers and about 100 million mentions of people. And our processing then yields 13 million research paper entities and about 1.5 people entities. And we've implemented something that's parallel, not at your scale, but at a scale that works for us, and has been quite tractable. And what are some of the ingredients of making this scalable? We avoid calculating 100 million squared edge distances using a blocking method that we call canopies. That is a soft method of pre-partitioning the data into mentions that have some similarity to each other, and the method leverages inverted indices to do so efficiently. We use some nice graph partitioning methods that are fairly efficient, and a very nice and important aspect of how the method works is that previous resolution decisions can be revisited and changed given later decisions and evidence. So it's not a greedy inference method. And so the resulting system is called Rexa, available through a web page that looks like this. You can enter a query in that box and get back a list of hits looking like this, where you see automatically extracted titles and authors, venues, years, abstracts, etc. You can click on a title of one of those and arrive at an automatically generated homepage for this paper, which shows you the full abstract, the outgoing references at the end of the paper, incoming citations from other paper that cite this one, a BibTeX entry, as well as topic labels that are automatically assigned to, discovered and automatically assigned to these research papers. And unlike Google Scholar and others, people are first-class objects. So I can click on Bruce Croft's name here and arrive at an automatically generated homepage for this person, including contact information extracted from his web page, all of his publications currently sorted by date, I could sort them instead by by citation count to find his most highly cited papers. Here I see his co-authors, currently sorted by the date of their most recent co-authorship event. But I could also sort them by number to find out, well, who does he co-author with the most? I can also find not co-authors, but cited authors. This is who does Bruce Croft cite when he writes research papers. And it's true of just about everybody that you cite yourself the most. It's not at all uncommon. We can also look at who cites Bruce Croft. And find well, and again, naturally it's true that people are cited by themselves most often. But it's interesting here. We can see that. Let's see here. Where is this example that I wanted to find? So one of the people that Bruce cites is Hector Garcia Molina, a professor who does work in databases. And one of the people that cites Bruce Croft is Doug Ord, a professor who does work in NLP. So we get some sense of where Bruce sits in the research community, sort of taking ideas from the database community and delivering them to the NLP community, which is a reasonable summary of a certain aspect of his work. Other papers have extracted grant pointers. So we do information extraction from the acknowledgements paragraph at the end of the paper, find references to grant, and we've imported all of NSF's grant database. So here we see this paper is acknowledging this grant. We can click on that grant and arrive at the homepage for a grant. It gives its abstract, its various award number, the list of PIs, and the list of other papers that also acknowledge this grant. So NSF is very interested in tracking the impact of their various funding activities, and this gives them a way to do that. We can also search for people. Here I searched for machine learning and reinforcement learning and got a list of people who would be experts in this field. And I can also look at topics. These are automatically generated home pages for topics where we run these Bayesian topic models on the entirety of the text in our collection, automatically discover that there is such a thing as this topic information retrieval as described by these lists of keywords and individual words and phrases. Here's where this topic sits in relation to others, other topics that are citing it and are cited by it, as well as the top papers that fall in this topic by various criteria, as well as its profile over time. So, it's a little bit hard maybe to see the trend, but it's possible that this research, at least the citation patterns or the number of papers, peaked during the internet boom time, and there might be a little bit of a dip.
We should finish up.
Okay, yep. On the other hand, neural networks is really nobody cares about neural networks anymore. Okay, so we've been looking at trends of idea flows through networks, and with that, I'll wrap it up and take questions if there's any more time. Thank you.
Just a quick question. If you wanted to do your co-reference resolution on something like a large-scale collection of documents or news articles, would you first do it on the articles and then somehow do it later globally, or would you try to churn the whole thing at once?
I think that there'd be some benefit to doing it jointly, where you didn't commit to within document entity resolution and lock that in before you went off to do cross-document. But my guess is that would yield some efficiency, which would not be a bad first approximation. Yeah.
We should let people go and then take the rest of the questions offline, because people probably have meetings and other various commitments. But let's thank Andrew again.
Okay. All right. Okay. Thank you.